Good morning. I am Adam Gao, and the project I'm researching is on finding the optimal location for wind farms in Colorado. This was mentored by Christopher Krause. And for the past 2 centuries, there has been increasing global demand for energy. And to meet that demand, carbon fuels have been used. And as attention is brought to the harmful effects on the environment, there has been an increasing demand for renewable energy. So in 2004, Colorado was a gentleman, and he said that there would have to be a certain percentage reached by energy utilities in Colorado by a certain years. So as of 2004, there has to be 10% renewable energy by Colorado energy utilities by 2015, and 20% as of 2013 by 2020. One really promising source of renewable energy is wind power. In 1980, on large-scale wind farms, it was about 35 cents per kilowatt of energy, and it decreased to 3 to 4 cents per kilowatt in 2004. So we used geographical information software, and it stores, it analyzes. You can manipulate information on there and create different maps to layer upon each other, work with each other to find different locations, eliminate unsuitable areas, which I'll talk about later. The software we used was ArcGIS by Esri. So we use two types of maps. We use constraint maps and we use graded scale maps. So with constraint maps, we eliminated unsuitable areas completely, and we left suitable areas to be graded. They were vector graphics map, and essentially what that is it uses geometrical primitives. It tells the maps instructions on how to make polygons, drawing lines and curves. So instead of pixels, you use instructions on how to draw shapes. And the reason we use that for the constraint maps was so that you could name certain polygons as their own areas. Like if you couldn't build on a wind farm on a certain national reserve because it was deemed unsuitable, then you could just name that as one big polygon. In addition, you can only, I'll talk about it later, but you can only buffer vector graphics-based maps, as in if not only can you not build on a certain area, but also a certain proximity to certain areas would be deemed unsuitable to wind farm development. And you can buffer vector-based maps because you can increase the distance or proximities required to lines as opposed to pixels. And pixel maps are raster maps. Each pixel on the raster maps represented 30 by 30 square meters in Colorado. And the reason we use raster maps for grading, what we did was each individual pixel we graded it in certain criteria for suitability of wind farm development, and that included wind power and land cover. So the scores of each pixel and of the specific criteria were multiplied together for a total score. The higher this score, the more suitable to wind farm development the pixels would be. So there are multiple roster maps. There are pixels, and each pixel was graded on a scale. Red, for all the roster maps, red was the most suitable for wind farm development, and green was least suitable. You can see the different lines and curves that were used to draw the vector map. So binary classification on the constraint maps, places were either deemed unsuitable or suitable. And there are required distances from certain areas for wind farms. For example, certain areas that required ecological protection and places that people attended to for recreation, such as national trails. And the reason that wind farms had minimal required distances from certain locations, and when we were mapping out optimal wind farm development locations, was well, certain areas would be unsuitable to be built upon because lands would be unstable. For example, you can't build a wind farm too close to a river because the land is unstable, or you can't build a wind farm too near to a city because, I mean, it doesn't necessarily affect different aspects of the the wind power efficiency of the wind farm, but there is public opinion, and some people don't like to see wind turbines near their homes. There was we had minimum proximity to certain locations by wind farms, power lines, and roads. It'd be more cost efficient to build near roads and be more cost efficient to power lines. Roads was a special case because you can't build too near them or too far from them, and that was something interesting in our methods. So for the roster maps, we graded them on their own scales, green being least suitable and red being most suitable. Wind power classification at 50 meters, you can see that most of the highest amount of wind power was in the mountains, but that was completely eliminated. You'll see later by constraint maps on slope. And so most of the suitable area in terms of wind power at 50-meter elevation was in the eastern part of Colorado. And there we also mapped land cover. Certain types of land cover was more suitable to wind farm development than others. Forests, they have high friction to wind power, and so that makes wind power less efficient. And you can't build wind turbines in water, obviously. Wind turbines are best built in grasslands or cultivated crops because in grasslands, even though they're extremely viable for wind farms to be built upon, where there's a lot of wind and little friction, you do affect the ecological situation, while in cultivated crop areas, the place is already used as farmland, so you can immediately return the location back to its original use when you have the wind farm building finished. And you can see here, we reclassified the land cover as the original land cover. Then each pixel was graded. And we multiplied the pixel scores of wind power classification and land cover classification. And this is what we got. Ignoring the mountain range area, the most suitable areas are in eastern Colorado. So we had 18 constraint maps that we used in our analysis, and so I'll just give a few examples. National forests was ecological concern, so and aesthetics. You don't want to. There's a minimum distance from them, and you don't want to build too close to them for reason of protecting the aesthetics of the location and the ecological situation. Same thing with bird areas. There are locations that you, if you were to build a wind turbine where areas with a lot of birds, there is a mortality rate, and they fly into wind rotors and they die, and that is not good as far as wind power efficiency is though. So karst topography, that's you don't want to build wind farms in unstable areas. This is not to protect the environment as much as it is to protect the wind farm locations. So you don't want to build in areas where there's potential soil erosion. That's unstable. And you don't want to build hydrogeology. We mapped rivers and lakes. Some rivers are more unstable than others. For example, some rivers, they're not wet all year long. They dry up. But nonetheless, we had minimum distances to all hydrogeology by wind farms. And you don't want to build in unstable locations. So slope, that was what eliminated the mountain range. If an area has more than 10% slope, so you don't have flat land, it's unstable land. And in airports, that's for the sake of the airports, not the wind farm sites, because you don't want wind turbines affecting the landing and the takeoff of the planes. And once again, unlike the other constraint maps, we had two minimum proximity constraint maps where the wind farms had to be close to certain areas as opposed to far from certain areas. As I said before, you want to build near roads and you want to build near transmission lines. And this is what we got when we overlaid the constraint maps over the roster maps. You can see the red circles are already pre-existing wind farms, and there's a lot of orange suitable area to the east where there is no constraint. And to the top east, you'll see this little area, Sedgwick County. That's where we decided where there are no previous wind farm development, but it's suitable. And here's Sedgwick County. There's a lot of nice orange area. And Sedgwick land cover, there's a lot of cultivated crop area. And when we reclassified it, you can see there is a lot of red. And this is a very suitable location. And here is the wind power classification. You can see ignoring the mountain ranges, which we eliminated, to the east, there is the highest wind power was rated about a 5 or a 4, yellow, and Sedgwick County is yellow, so has a lot of suitable wind power. And my acknowledgements. I'd like to acknowledge my mentor, Christopher Krause. He did help me a lot. He explained a lot of things to me, and it was fun working with him. My advisor, Scott, he gave me a lot of information. I thank you very much for actually living with us in the dorms. That was a lot of help. It was great to be able to ask you questions when needed. Could see other people appreciated it too. And my research sponsor, Excel Energy, and my scholar sponsor, the 1984 FSI alumni, and FSI staff for having me here. This was a very useful camp. And yeah, I'm gonna keep it on here.